As we saw in the last video when we looked at maple, we realized that there are actually higher order partial derivatives as well. So we want to see how these work and how they relate to each other. So how would fxy work, for example? That would be the partial derivative with respect to y of another partial derivative that you've already taken with respect to x of the function z. All right, so let's see how this works in practice. So we have this lovely function right here, f of x equals 5x cubed minus 7xy to the fourth plus 2y squared. So I'm going to start off by taking the partial derivative of this with respect to x. All right, so that would be 15x squared. This part, the 7 and the y to the fourth are constant, and the derivative of x is 1, so it's just 7y to the fourth. And then this part, it's constant, so its derivative is 0. All right, similarly, let's take the derivative with respect to y. So that would mean 0 here, so there's no y in that term, minus 7 times 4, so negative 7 times 4 is 28. There's an x, and then y to the third, because you're bringing the power down and subtracting 1, plus 4y. All right, now what if I take the derivative of that function with respect to x again? So the derivative of this with respect to x would be 30x, because there's no x in this term. What if I took the derivative of this derivative with respect to y, and took another one with respect to y? So y and then y again. So that would be, well, the 3 comes down. 3 times 28 is 84. So 84xy squared plus 4. All right. Now let's take the derivative of, well, derivative with respect to xy. So we take the derivative with respect to y of the derivative we've already taken with respect to x. So we want to take the derivative with respect to x, which is right here, and we want to use it to take the derivative with respect to y. So the derivative of this bit with respect to y is 0. And the derivative of this bit with respect to y is negative 28y cubed. All right, what if we want to go yx? So take the derivative with respect to y and then take x afterwards. So that takes this part, fy, and now I take the derivative of that with respect to x now. So the derivative of this with respect to x is negative 28y cubed, and the derivative of this with respect to x is 0 because there's no x in that term. Hey, they're equal to each other. Interesting. And that leads to this bit right here. So if f of xy is a continuous function, then equivalent mixed partial derivatives are equal to each other. So if you think about what we just saw, equivalent mixed partial derivatives, we just saw, for example, fxy is equal to fyx. It doesn't matter which one you do first and which one you do second. So as long as you have equivalent mixed partial derivatives. So a mixed one, so meaning that you have x and y, not y, and x, because those are not the same, right? But if they're mixed and they're equivalent, i.e. just one x and just one y, then it will work out. And it actually doesn't matter which way you go. All right, so let's go a little bit further. What about fxx? Fxx. So I take fxx, and I take another derivative with respect to x, and that would be 30. Or if you like, here, let me write this out. What you're doing is you're taking the partial derivative with respect to x of 30x, which is 30. Fyy would be the partial derivative with respect to y of fyy. Oh, sorry, fyy is the partial derivative of that. Oh, and fyy was, I'll just put it in. It was negative 84, it's this one right here, negative 84xy squared plus 4, which would be, let's see, negative 168xy, because the derivative of 4 is 0. All right, so those are obviously not the same, right? X is not the same as y, x is not the same thing as y, and so on. But what about the mixed ones down here? Let's see. So I want to take xy. So I take x, which is 30x. So this is the partial derivative with respect to y of fxx. which is the partial derivative of this part right here, which is 30. So that would be 0, right? Because there's no y in that. And then xy(x), that's the partial derivative with respect to x of fxy. So that'd be the negative 28y cubed. And the derivative of that with respect to x is 0 because there's no x in that. Or fyx, that's the derivative with respect to x of fyx. Okay, so yx is over here, negative 28y cubed, and the derivative of that with respect to x is 0. So they're all the same. So not only are fxy and fyx the same, but we also learned that fxxy is the same thing as fxyx, which is the same as fyxx. So by mixed, oh, I should say equivalent mixed. Equivalent mixed. What does that mean? Well, we could have one x and one y. We could have two x's and one y. And I'm willing to bet it's going to work for two y's and one x, but let's prove it up here. So if I look at fyx, so that's the partial derivative with respect to x of fyy. Fyy is right here. So I'm going to take the derivative of that with respect to x, and that would be negative 84y squared. All right, what about fyx? That's the partial derivative with respect to y of fyx, but fyx is right here, and 3 times 28 is 84, so that's negative 84y squared. And then fxyy, that's the partial derivative with respect to y of fxy. Fxy was over on this side, and sure enough, they're all the same. So not only is it working for two x's and one y, but it's working for two y's and one x. So it doesn't actually matter with partial derivatives which one you do first, which one you do second, just as long as you get the number that you are looking for. And I believe I can prove this with Maple. Let me pull Maple up really quickly. So I named my function f6 because it's the sixth example, so I just called it f6. And I said take the derivative with respect to x, take the derivative with respect to y. And then I had it take the derivative of this, which was fx, partial derivative with respect to x. And I said, hey, take the derivative of it again, but now with respect to x again. And so there's the 30x that we got. And then there's the negative 84. And you can just keep going and going and going. I mean, if you want to do multiple derivatives, you can also use the delta palette. So it kind of doesn't matter which way you go. Me personally, I really like the diff command, but that's just me. You could also tell it to do multiple derivatives at once. So rather than doing it this way, so let me show you. So I did fx right here, and then I said, hey, take the derivative of that again with respect to x. That's a little long and cumbersome. So what you can do instead is say, hey, take the derivative of that. And if I just say x with a little $sign and then 2, it'll take xx. If I do y with a $3, then it's going to do yyy. Right? So that was 168y, or let me show you. It was this one, yyy, 168xy. And then if I say, hey, what about x squared and then a y? So do two x's and a y, it gives me 0. And it doesn't matter, again, what order I go into. So I don't have to worry about whether that's xyx or xxy. It doesn't make any difference because they're all equivalent. And xy squared, right, xyy was negative 84y squared. And so on. Cool, huh? So I really like the diff command. It's just, I prefer it, me personally, to the palette command, even though this is more what we write when we write it by hand. You're saying I want to take two derivatives with respect to x and then with respect to y. And if you're thinking, well, does it matter if I do x first or y first? The answer is, it doesn't matter, right? As long as they're equivalent, it does not matter whether you do x first or y first and x first. And of course, you can always use Maple to back yourself up. It's not even really that difficult. Me personally, I'm very, very fond of the diff command. for differentiation.